from the mean, and that's how you can apply parametric testing. If you don't have that normal distribution, you can still do statistical testing, but you're going to have to use different types of methods. So you'll see later on, for one of the tests, I haven't used parametric, I've used non-parametric tests. But the parametric ones are the ones which are more powerful. They allow you to extract more information from the data. Okay? Now, one of the things you can do is a power test, and you can do this before you do the test or after you do the test. If you do it before, you have to estimate things about the data, which is obviously another kind of rule of thumb. You say, well, my variance is going to be around there, and that you might be totally wrong. But it's a way of giving you an idea that you need 50 and not 500 subjects. You might still be wrong. But you can also do a test afterwards. So let's say you bit the bullet and you've used 30 subjects and you come up with a result, and the result tells you that you cannot reject the null hypothesis. Now you're faced with a big problem. You don't know if you're rejecting the null hypothesis because you haven't got an effect and people really cannot detect the difference between, say, the two conditions or more, or because there isn't enough data for you to be able to analyze that. And a power test will tell you that. So if the power test will come very high, say 0.9 or above, it's bounded between 0 and 1. If the power test comes up very high, then you know that you've rejected the null hypothesis because there is no difference between the two conditions. If it is low, you don't know, and that's all you know, and it ends there. You need to repeat the experiment with more subjects or rerun a better experiment. Okay. Then you come to this kind of, what type of testing am I trying to do? There's different kinds of tests out there. A lot of the testing methodology and techniques are actually borrowed from the food industry, funnily enough. So in audio, we use a lot of the techniques that have been used by the food industry, in many years in the past. But usually, if you're going to do subjective testing, the first branch is whether you're going to be using trained panels or whether you're going to be doing a consumer test. There's a big difference between them. Basically, if you're trying to find out detail about the property, perhaps describing properties of the product, say, that a loudspeaker A is smoother, is more rounder sound, or whatever that might mean, or that MP3 sounds digitized or sounds quieter. You're trying to find out about particular aspects of the product, of the conditions you're trying to do. And for that, you've got a couple of ways of testing. One of them is called sensory profiling, which is where you basically get the stimuli to the subjects, but you ask them to tell you what they feel about it, whether they feel it's harsh or smooth or quiet or whatever. So you don't tell them how much of this scale they think it is. You basically ask them to tell you what are the words that elicit the feeling that they got when they were listening to it. Okay? Now, usually, if you want to do that kind of testing, you don't need a lot of subjects. You need about 10 to 15, but you need to train them in the activity that you're doing. So you need to explain to them, this is the kind of stuff we're looking at, this is the type of variation in the conditions you're going to listen to, and I want you to tell me some of the words, and then you meet up with them again, and you try and see whether, José, who told you that it was kind of smooth, agrees with Antonio, who told you that it was actually round, and smooth and round mean the same thing. So you start bringing those terms down. Or you can go on to a different kind of branch, which is called difference testing, sensory difference testing, which is basically you present two conditions and you ask them to tell you whether they can detect the difference between the two. Again, you're doing that with trained listeners, so you're hoping that they're going to detect the most minute differences. Now that's usually what you do if you're developing a product before you put it on the market. It's what you do as a company if you're trying to find out what are the different things that you can do to your product to make it better, to make it sound more like this or more like that. And that's what you would do if you were starting some research into a certain new area. But once you've got that profiling done, once you understand more or less how you can control your conditions, then you want to try and prove it for the wider audience, for all your customers, everyone that might be buying the product. Or if you're doing research, you want to see if you can generalize across a bigger audience. So that's where you do this consumer type of testing. And here, we're talking about this thing, hedonic or affective test, and that's really how good does it make you feel? Is that better than that one? Would you buy that one if it cost the same? That kind of question. Now that, you identify the kind of preferences. I don't think you can see very well the slide because I can hardly see it here, but it says preferences, trends, and market studies. So that's what kind of tells you what the general population might do when looking at your product. And of course, if you're going to try and do that, you need a lot of subjects. You need about at least 100 to 150, and I call them naive listeners. That means they haven't been trained. They don't really know about the artifacts that you're trying to test. They're just listening for it in a general way. Okay? So they will be like customers. Okay, now this is the kind of stuff that I've been describing, so I won't go through that. When you're doing discrimination tests, there's a number of really neat ways of doing it, kind of proven methodologies. There's a few I like. For instance, this ADX one is one that we will see in an example a bit further on. ADX is really simple. What you do is you've got this sort of little algorithm that picks up the two samples that you want to test, A and B, all right? You know, one has been encoded, the other one has not. They've been normalized in terms of level. And then at random, it picks up one of these and puts it in this button X as well. And the subject can either press A, B, or X and listen to them. And the answer you want from the subject is whether X is A or whether X is B. Now, if they give you the right answer many, many times, then you know that subjects can detect the difference between A or B. All right? Now, that's a little bit better than to just present the two buttons, A and B, and ask the subject, are they different or the same? Right? It's a different question. And this is one of the key things about subjective testing. You need to make the subject feel as much at ease as you can. You want them to give you the kind of the correct answers from their perception point of view. You don't want them to be cognitively engaged into thinking, oh, you know, is it different or the same? I'm not sure, and then give you a wrong answer, for instance, because they're not sure. So this is a kind of a better way of testing. And, you know, you do a number of tests and you do some stats. Binomial distribution is the one that you use here, and it tells you the probability that the subject was guessing or that they could indeed detect a difference between the two samples. And, you know, so that's a statistical result. You could also go for just preference. So here, we're not asking whether they can detect the difference. We're asking whether they like A more than B, for instance. And that's, again, very easy for a subject, because if it's just preference, they'll just be able to respond quite simply. And then there's a number of statistical techniques that you can apply to kind of detect that. Most commonly, you'll be looking at this kind of test, rating based, and that's where you've got a scale. 0 is really bad, 5 is really good, and you just ask someone to listen to your loudspeaker and tell you on that scale where they think the loudspeaker could be. 4 or 5 is really good, or say 0 or 1 is really bad. Or you could have a ranking based, which is you have loudspeakers A, B, C, and D, and you ask the subject to put them in order. B is better than C, which is better than A, which is then better than D. So you've got a rank order, but you don't really know whether the differences between them are equal or different. So you just have a rank rather than a continuous scale. And for all of those, you can use, you know, different types of techniques. So for instance, you can do paired comparison. Let's say you need to test 10 different loudspeakers. Ranking the 10 would be really difficult for a subject. So one of the options you could do is you could ask them to do a paired comparison between all the possible pairs. Now in 10, you've got a lot of possible pairs. But you could do that many, many times and then apply the Thurston type of analysis, and that would then give you on a continuous scale where, for each subject, the loudspeakers will be placed. And that's a really neat way of testing things. I've used that in the past. And it was, you know, it was quite interesting. So what you're doing there is you're asking a really simple question from the subject, but getting a lot more data from the responses. And that's one of the key things about perceptual testing is make it easy for the subject because you get better data. So these are some examples of rating-based scales. So we've got, these are all on the ITU P800, which is a telecommunications standard for testing communications over, for instance, telephonic lines. You've got things like absolute category rating, which goes from bad to excellent. Or you've got stuff to do with degradation that says degradation is very annoying, degradation is slightly annoying, degradation is inaudible. Or you go, okay, how do these two sounds compare? Well, sound A is much worse than sound B, or they're about the same, or sound A is much better than sound B, and so on. So all of these scales you'll be able to find in the standards, and of course, depending on your test, you will choose one of these scales, okay? And of course, that will then affect the statistical analysis that you can apply, the type of results that you can get out of it. This one is perhaps one of the most common types of testing in audio, and it's one of the ones I hate the most. It's called MUSHRA, which stands for Multiple Stimuli with Hidden Reference and Anchor. And it's basically this. You've got a reference which is what you would say the best quality possible for whatever condition you're trying to test. And then you've got a lot of unknown samples that you can listen to. And the subjects can always compare the reference with each of these samples. And what you want them to do is you want them to tell you whether each of these samples sound much better or about the same or much worse than the reference. Or you could have a numerical scale between 0 and 10 here, okay? Now, what the subject is supposed to be doing is comparing that one with the reference, then that one with the reference, then that one with the reference, and so on. But what the subjects end up doing, and that's more or less the idea of the test, is they do compare each of them with the reference, but they also compare them between each other. So you start getting this kind of ranking or even ratio location of the different samples. Now the trick in this test is that you've got a hidden reference that is one of the versions of the reference is going to be somewhere here, and you hope your subject is going to be putting that at the maximum. And you also have a hidden anchor, which is one of the samples that sounds really bad, noticeably a lot worse than any of the others. And you want the subject to put that one at the bottom of the scale. And that allows you to use the entire range of the scale. You force the subject to use the entire range of the scale. Now, what you can do is you can do a check for how good your subject is. If, when you come to look at the subject's results, there's no sample at the top and no sample right at the bottom, they haven't found where the reference and the hidden anchor are. So they're not good subjects, they're not accurate enough for your test, and you could probably discard them, right? So that's one of the tricks of the test. Now, the reason why I find this test really bad is because, let's say you've got these 7 samples to compare, and you've got a number of these panels. In this case, we're in experiment 1 of 3, which means we have at least another 2 of these panels. You're going to get your subject to keep on doing paired comparisons all the time. And after a while, your subject, who has been doing, okay, that's about the same, that's a bit better, that's a bit worse, that's better, oh, but now I want to go there and push this one up a bit because this one was around there. And this one is much lower, so I want to push that one up a bit. And you start getting your subject to keep coming back and changing the settings, which is fine, that's what you want to do. But the subjects will get tired, and at some point they'll give up. They'll go, the heck with this, I'm just going to go to the next one. So you leave a lot at random. You allow a lot of noise to come in because subjects will start getting fatigued and they will move on, all right? And that's why I'd rather prefer paired comparisons between just 2 samples all the time than one of these. But they're very popular, so it might be something that if you do subjective testing, you'll come across. A numerical continuous scale is probably the simplest. You hear a sound, I want you to tell me in terms of direction where that sound is by making a mark on this graph, 45 or around there, or at 90 or around there, okay? And that's just a numerical scale. Okay, and as I told you before, when you do the experiment, you do have to document everything, just in case you need to go back to do the analysis, or you need to set up the experiment again, or someone else wants to do the experiment like you did and test your results. So everything needs to be properly documented. Good. Okay, so that was the kind of introduction. So I'll just go through a couple of research examples that I've done in the past that use some of these ideas. This one is kind of quite fresh in my mind because we've just been submitting a paper to the Acoustical Society of America on these results. This is basically after I got my PhD in 2004, so it's 11 years ago. And it was basically what I wanted to do in my PhD. When I got to the end, I realized, after having done all these things, this is what I should have been measuring. This is what's important. But I never got to do it. And then I got a PhD student who did all his PhD and right at the end managed to measure that. And then he went to work, I kept on doing my work, and the whole thing was kind of laid down for years and years until finally I found the time to get all the data and write it all up. And so you're basically looking at very, very fresh results. And it's basically looking at the perceptual effects of modes as a function of modal decay. Now raise your hand if you know what a room mode is. Okay? That means I'm going to have to explain it to you. Some of you do, yeah? Did you know? No? Okay. Quite simple, you'll all have been exposed to room modes. Have you ever sang in the shower when you go in the bathroom and you go boo-doo-doo and it's really echo and reverberant? That's room modes. They are resonances and they kind of help your voice. Now, it's not the same as reverberance, which is what we kind of hear here. It's reverberance but at the low frequencies. So it's kind of woo, it's booming. So, room modes are basically standing waves. We're not going to go into the physics of it, but they basically excite specific frequencies and they're related to the size of the room you're in and where you are and where the microphone is, where the loudspeaker is and the microphone is, okay? So what do they cause? Well, if you were to measure the frequency response, the spectra at a certain position, having put a loudspeaker in some other position in the room, you would see that across the frequency, you would have the level of sound varying quite a lot, where these peaks are basically resonances. They're the things that you would hear if you sing in that space. So they cause that. If you were to walk around in the room from one end to the other, and you were to excite it at one of these frequencies, you would see that, say, near one wall, that sound would be very loud. Somewhere in the middle, it would be very quiet. And then again, at the other side, it would be very loud. And that's just the first mode. The second and third modes would have other dips within the room. So they're quite problematic. Because imagine you're dealing with this in a monitoring room for a studio, for instance. Okay? The other thing that they do is they affect the sound that you place through the room. So they affect the sound of the room when you're listening to, say, loudspeakers. So room modes are basically critical if you're in a room where you're trying to mix music and say, you know, you have a mode at 80 Hertz, which is the bass note, and there's a song with 80 Hertz and you're playing that, and, you know, some people are there going, ooh, that sounds a bit odd. Well, it sounds odd not because of the recording or the mixing, but because of the room. So we wanted to investigate people's perception of that problem. I'm going to try and give you a few examples then. So here's a room, and we're looking at a loudspeaker at a certain position, and a listener, which is sitting in what we call the sweet spot. Do you guys know what the sweet spot is? In a studio, that's the critical point for getting stereo in between the two speakers. So this is what the sound engineer gets when he sits in the sweet spot. Listen to the bass. Once again. Okay, but in this studio, there's a producer who is paying £5,000 a day. Okay, how much is that in pesos? 5 million?
4 million.
4.5 million pesos to use your studio. You're sitting there, and this guy is paying for your work, and he's sitting here, and this is what he's hearing. Here's a comparison. Can you notice the difference? The bass notes, especially the kick drum, lose a little bit of the definition. It's not very good in the center, it's not very good there, but it's much, much worse there. And we can see the response of that room in here, we can see that, you know, the modes decay with different times. For instance, here, we've got these modes decaying for a much longer time. That means that the producer is probably going, this mix sounds crap, it's really bad the work you're doing, I'm not going to pay you. But this guy is sitting there thinking, the producer is mad, the mix sounds perfect, or at least it doesn't sound that bad. The reason why they're both getting a different perception is because they're being exposed to the room modes in this room. And therefore, each of them is actually listening to a different mix. So we want to study how much people are sensitive to these decays, and we want to find out where the thresholds are, so that if we were to treat this room, we would make it so that there is no difference between these two cases, but not any more than that. So we wouldn't bring in more absorption, we wouldn't use much more of the space area of the room, and we wouldn't spend as much money. Okay? So the idea is to try and find where are the thresholds of differences between these two cases. So obviously we're going to try and absorb the modes up to a point where people no longer perceive the differences. That's the key thing. So this is basically what I've been saying. So we're kind of interested in the response of listeners to the manipulation of a factor. In this case, what we want to do is we want to identify the factors we're going to control. And for modes, you've got amplitude, center frequency, and Q factor or decay time. We're going to do an experiment where we vary the decay time. So the decay time is going to be one of our independent variables. Okay? Sorry, completely wrong, wipe that out. The decay time, which is what we're going to measure in terms of thresholds, is going to be a dependent variable. It's what we're going to get from the subject. It's where they say, I no longer hear the problems of that mode. So it's going to be a dependent variable. We're going to have to look at what the independent variables are. So, what are we interested in? We are interested in the thresholds of detection for the effects of modes as a function of modal decay. So here's the dependent variable. But we also want to know, how do they vary across the frequency? Now we can control that. We're going to call that an independent variable. We also want to know, how do they vary with presentation level? Whether it's going to be different if we play it very loud or very quiet. Another independent variable with basically two levels. And we also want to know how the thresholds vary, whether we test them with some artificial stimuli, which is properly designed for testing, or whether we do a more ecological valid test where we use music. So we've got two different types of stimuli, artificial and natural. And that again is another independent variable. Okay, so in terms of test design, here's the stuff that we've used. The artificial stimuli was basically a little sine wave that's going at a certain frequency, going boo, like that. And then we put the modal decay right at the end. That's more or less what modes are. They're kind of resonances that have a single frequency, as you've seen in the waterfall plot, so they will decay with a certain decay time. So this is what we call the artificial stimuli. So that would be our baseline, which is no decay whatsoever, just the sound. It's got to be windowed so you don't get any artifacts. But that decay there is too short for anyone to perceive it as a decay. And then what we do is we add the decay that would come naturally if this was a mode. Okay? So that would be our baseline, our reference, and this is the modal decay added on. But we also want to test that with music. So in this case, we've chosen two different types of music samples. We've got 5 seconds of each here, and this is a spectrogram, so it tells you where the energy of the music is. We can see that, for instance, this one, which is the one we've been listening to, goes boom, 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 doo, which is what we've been hearing. So there's the bass notes there. This one is a kind of a jazzy sample, which has got a lot more bass going on. It's a walking bass. And we're trying to see that because we want to measure whether the music stimuli is going to have an effect or not on how, we measure the thresholds. So the independent variables, as we said. And we're going to present this as two levels, as I said before. So we want to present this to subjects over headphones, because that's good. We don't get any of the room modes of the test chamber that we're using. We want to present it over a number of conditions. We want to identify the independent variables, which we've been doing. We want to identify the dependent variable, which is here. And of course, now we need to somehow find a way of testing this. Now, in most cases, what we do is we model the response and we present it over headphones. Okay? So how do we model the room? Well, in this case, because we can look at a very simple rectangular room, we can just use an analytical model of a rectangular room, which is called the Green's function, which basically gives us the response according to some parameters of the room, its size, the amount of absorption, where the source and the receiver are, and so on. And of course, before we do anything, we need to test this model against the measurement of a room, which is what we've done, and we can see that for the purposes of our test, the agreement is fairly good. It starts getting a bit bad towards the high frequencies, but we're not trying to emulate a single specific room. We're trying to emulate room responses. So as long as this looks like a room response, then we're happy with that. So, you know, the model has got some limitations, but it's got a lot of advantages. It allows us to very quickly, very simply control some of the parameters of the room and create a response. Okay, so here's a demonstration of how one of these models would work. So this is the kind of stuff that you would get if you code this in MATLAB. Here, listening to the artificial stimuli, and that would be the reference at a frequency of 100 Hertz. So just a single tone going boom, like that. Okay, so that's the reference. And now try and have a listen to see if you can hear the decay imposed on that. Yeah? Hopefully you can hear a difference between that one and that one. You can see that there's bits of smearing in the initial part of the response. It doesn't have as much attack, and it's got a longer decay. And if I make it even larger, say, you know, over there, you can hear a difference. Yeah? So this is basically establishing that our model is able to create some kind of room response. You can see the example here, so that's a response up to about 300 Hertz. And this was actually used for a different experiment, but it's good to illustrate the effects. Okay, so what we do then is we have this model that you've just been listening to, and we can get, if we want to listen to music rather than just a simple artificial stimuli, we can get a sample, you know, any sample. That's the one we've used. So that's the original one, that's what comes out of the CD, and we convolve it with the response that you've just generated from the model. So you basically do a down sample there, so you don't need to deal with as many data points. You're just looking at the low frequencies. You convolve it. We need to apply some equalization because we're going to use some headphones, and you calibrate it so that it comes out at the right level when you present it, and that gets low pass filtered. So that branch there forms the low frequency response of the conditions that you're testing. And if you listen to it on its own, it sounds like this. So this is basically the low frequency response of the room itself. And what we're doing is we're adding that to the high frequency that's left from your original sample. This bit, okay? Now, why are we doing that? Well, we're doing that because this here is what we want to test, and we can vary this very, very quickly. So we can present a really boomy room very quickly after a very nice and dry room and ask people whether they can tell the difference. So the final sample sounds something like this. Okay? So that's the low frequency response added to the high frequency response and calibrated, and you get a room sample, an audition that you're going to use for your testing. Okay, so the way we've done this is, what we want to do is we want to try and identify a threshold. And we want to do this by asking people, we play them, say, a reference and a sample with lots of modal decay, and we ask them whether they can tell a difference. But we need to do that many, many times until we come to a point where they can no longer tell a difference. So we could start with a large difference and keep asking and keep reducing the difference and do, say, 225 auditions until we get to the threshold, right? Or we could try and aim for that threshold much more cleverly and much more efficiently. And that's what this kind of testing does. It's called the parameter estimation by sequential testing. And it's basically a set of rules that tells you, start with a really large difference, and then depending on the subject's answer, you change to the next sample accordingly. So you might make a big step jump or you might make a small step jump. And usually what you end up doing is you zigzag around the threshold very quickly, and in around 10 to 15 auditions you end up converging to the threshold itself very, very quickly. Okay? Obviously a lot more detail could be said about this, but you know, we're kind of running through. So if you want more detail, I can tell you at the end. We've actually established a way of deciding at each of these audition points whether the subject can tell the difference or not reliably by applying the trusted ABX testing that I explained before. So every time you need to make a decision, you ask them to tell you whether they can really tell a difference via the ABX testing. And we do that using 3 different auditions, 3 kind of comparison results. And if the subject is able to tell us correctly 3 times, then we move on to the next level. If they fail one of them, then we know they can't hear a difference. We take a different decision in terms of where to go on the test scheme. Okay? And by doing this, we know that we've reduced the probability of subjects guessing to about 12.5%. Because of course, if you ask subjects, can you tell a difference? There's 50% they could be right, and 50% they could be wrong. They could be guessing, and they could run through that scheme just guessing over and over and over, which is something we don't want, we want to avoid. Okay, so just with music, I think you might be interested in listening to how it sounds. So here's an example. If we run the music, so here this slide basically changes the modal decays, and you'll be able to hear the differences that the subjects were being presented with. So something like, can you hear the boom? I've done this test many times, I can hear it. But it's basically the difference between that and say that, which would be the reference. Now that first one was a large difference. Of course, our subjects end up listening to things quite close, say between this one and just slightly lower, like this one. Okay, so the good thing about the test methodology is that it starts with really large differences which are easy to identify, and then it converges to very, very tiny differences until you're at the threshold. And by the way, these are generated, so you listen to them over headphones. Of course, over speakers, it's a lot more difficult. And I guess that's why some of you might not be quite detecting the difference. It's because we're in a room with its own room modes, which again would be a problem for testing. So, results, finally. This is the kind of stuff that we've measured. We've measured this trend. We're looking at artificial stimuli. And we've measured that, at very low frequencies, then the thresholds, the detection point is really high. We can have decays up to about 1 second and people still are not detecting them. And look at the variance of the data. Subjects don't seem to agree very well. Some subjects will detect at about 0.75, whereas some subjects will detect only at about 1.25. And that's a big difference in terms of decay. But as we go up in frequency, then we start seeing that the decays reduce quite a lot. Now, in terms of stats, if you do the analysis of variances between, say, the frequency points or the different levels at which we've measured, you can see the 2 lines here, then we can find whether they were significant or not and how big an effect size that had. So, for instance, we can see that replay level is significant. It's got a probability of 0.0, below 0.01, so we know that replay level is different and excites different modal thresholds, but it has a very small effect size, which means it's not a very important aspect. But people still perceive thresholds differently, depending on whether you present it, a very quiet level or a loud level. But perhaps more important, this data is showing us that frequency is a very significant factor, and it has quite a large effect size of about 38%. So 38% of the variance in this data is explained by the differences measured across frequency. Now that's interesting, and we can see it in the graph, but the stats allows you to report it as actual results. So we can see that, there's a big difference between that result there and this result here. But because in my analysis I didn't have a 32 Hertz data for the quietest, because it was too quiet for people to even listen to, the analysis has only been done across this area of the graph. And what the analysis tells us is there is a significant difference between the thresholds at, say, 63 Hertz and the thresholds at 100 or 150 or 200. But I don't know exactly where those differences are. Remember, the ANOVA tells you there is a significant difference between one or more points and some of the other points, but it doesn't tell you where they are. If you want to do that, you need to do a paired comparison statistical analysis, which needs proper correction, so you need to kind of factor that in. And that will then tell you where the significant differences are coming from. And in this case, it's telling us that there's a significant difference between the levels measured at 63 Hertz and the levels measured at any of the other higher frequencies, but no more differences between any of the higher frequencies. So the difference is basically at 63 and then above 100. So what we said here is that the result sort of converges to about 0.2 once you're above 100 Hertz. So that's your threshold from 100 Hertz and above, only up to 200, which is where we've measured. But if you go below, then the threshold goes up. Okay? And what that is saying in practice is, if you're trying to treat the room, if you want to treat it right down to the low frequencies, 62 and 63 and 32, you need to put a lot of absorption. Sorry, you don't need to put so much absorption because the thresholds will increase. That means people are no longer sensitive to them. But if you want to try and treat down to 100, then you might need to reduce the decays accordingly so that no one notices the difference. But these are results for the artificial stimuli. We're perhaps a bit more interested in what happens if you're listening to music, because that's what people listen to in these cases. So these are the results with music. And again, we've done the stats analysis, and we've got a significant effect reported for frequency. So you can see that that p-value is below the critical level. And we see that the effect size is actually quite large. It explains 50% of the variance in the data. So it's telling us that frequency is what causes most of the differences across the measurements. And what we can see here is we can see the results for 75 dB replay level and 85 dB replay level. And when we look at the result for frequency, what that is telling us is that there is a significant difference between what we measure at 63, what we measure at 125, and what we measure at 250. And we have done a paired comparison between the frequencies, and it told us that there is indeed significant differences between each of them. So it's not the case that we found with the artificial stimuli. In this case, we're finding differences between each of these frequencies. So it kind of gives us a map of how people perceive the thresholds across this range of frequencies. It also tells us that replay level was not significant, and that's interesting. So it's basically telling us that the data on each of these graphs is basically reporting the same. And that again is different from what we found with artificial stimuli. So for music, the level difference is no longer a problem. So the decays, the thresholds for modal decay will be the same regardless of whether you play it loud or quiet, which is an interesting result. And then finally, we've got a significant effect reported for sample, telling us that testing with a certain type of sample or testing with another type of sample leads to different results, but the effect is very, very weak, only about 7%. So that's telling us that the type of music you choose to use in the test is relevant, but not as much as, for instance, varying across the frequency. Okay? But it's kind of warning people doing this kind of research that testing with one single sample might not be sufficient, that you need to find different examples. Okay, so what's the conclusion from this work? Well, what we've tried to do is we've tried to map these thresholds in order to give people some kind of guidance. When they come to design a room, who is designing the room? Our colleague back there. No, that's not you. I think he's left. Oh, there you are. Sorry, you're designing a room in your home, isn't it? Yeah? So this kind of thing would be useful for when you come to do the treatment of low frequency, because it tells you if you measure your room and any of the modal decays, any of the decays in the low frequency are above this line, then you will be hearing the effects of the modes and they will have an influence on what you mix in the room. Okay? So if you wanted to treat the room, you would have to make sure that it's treated so that the low frequency reverberation, let's call it, is below that line. But that works well if you're listening to music. If you want to be very, very critical and say this room is absolutely clean, it's got no problems with room modes, then you'd probably need to aim for this other line, which is the line that we've measured with artificial stimuli, therefore much more critical. So those with very critical ears would actually detect modes in this region, but perhaps not much below that line. And then finally, we've left the lower 95 confidence limits for the very, very critical listeners out there. The guys that go into a studio and go, ooh, there's a problem with the room mode around here. Those, if you wanted to build a studio for them, you would probably need to treat the room so that it's below this very faded line. It's much better on my slide, but you need to treat it below that point. And below that point, you can be very sure that only 5% of the population, at least the one we tested, would be able to detect the modes. And that's kind of the whole point. Okay, so that's the end of that. I am thinking that probably you are very tired, and I have one other experiment which is actually quite interesting, but it won't be of any use if you're all very tired. So what do? We've gone for about 1 hour and 10 minutes now. What do people feel like? You want to continue?
Yeah. Carry on? Yeah? Okay? Yeah. Maybe wrap it up a little bit so we get some time for questions.
Okay, I think you'll like this one, because this is some of my more recent research, and it's not as intricate as the other one. So here, the interest is in looking at when we listen to sound over headphones, and we kind of make it so that, we try and oralize sound and use head-related transfer functions and so on. People are still saying that the sound is not quite out there, it's inside the head and so on. So I tried to look at something else that might be playing a part in that, and I called it plausibility. But basically the idea is, if you play sound over headphones, often you hear the sound inside your head, and that's quite clearly because we're listening to using loudspeakers to listen to sound, and of course we're used to listening to sound in the environment, which means that the interaction of sound wavefronts with our shoulders and our head and the position of our ears on the side of the head gives us an idea where the sound is, but also that it is outside. When you feed the sound directly onto the ears, the brain is not getting any of the cues of your torso and head and position of the ears, and therefore it needs to make sense of it. And so it doesn't sound anything like the other sounds it's been used to listening to. So it basically says it's not out there, it's got to be inside the head. And that's why we get that sort of percept. Now, what people try to do is they try to use these intraoral level differences, intraoral time differences between the ears, and spectral differences incited by the torso and the ears in order to make that sound being externalized, okay? There's been a lot of research onto that. So people know that externalization of sound over headphones depends on distance cues, reverberation, intraoral cues, spectral cues. It relies also on the reproduction, so whether we're using the head-related transfer functions of the listener itself rather than a generic one, whether we have head tracking on the headphones, so that when people move their heads, they go, ooh, that sound has stayed there, which means it must be outside because the sound on the headphones moves as I move my head, or even headphone equalization. Okay? So these are the kinds of things that people have been working on in terms of getting proper externalization over headphones. There's a lot of knowledge, a lot of publications out there on that. A number of people have started looking into this training, okay? Which is, you bring in a subject and you ask them, okay, where is that sound? Is it inside the head or outside the head? Is it at 45 degrees or at 90 to the right and whatever? And they give them a response, and then they feed back the correct response. They say, no, actually, that was outside and it was at 30. And they found that if they do that often, over a week or two, the subjects will start externalizing the sound. So they train and they start recognizing, actually, it is external. Oh, I can see it now, I can hear it. It's a little bit like these auto-stereograms that were out there in the 80s. These pictures with patterns that you look at them, and if you cross your eyes, you get a 3D image coming out. Have you ever come across that? Some of you might have. That's a cognitive kind of process. And I believe that externalization is a little bit like that. Once you start kind of focusing on the right cues, the thing appears. Well, I decided to look at something else, which I call expectation and plausibility. And it's basically the idea that we've been looking at the cues as being the most important aspect of getting externalization. But I've been exposed to situations where I'm listening to sound, sometimes over headphones, and then all of a sudden, it sounds like it's out there. You know, some keys jingling or a mobile phone ringing or something like that. And you're kind of going on, oh no, this was playing on the headphones, but it really sounded like it was out there. And I call that the plausibility effect, which is if you expect a sound to be out there, will you naturally externalize it even if you don't have the correct cues? So here's an example of that. Have a listen to this.
This is Bullet. He's actually a pretty nice dog.
But he's been trained to do this. We're going to make people think they're being attacked by him.
But it'll just be in their headphones.
Here's the setup. DTS has developed a technology that creates a realistic 3D-like surround sound experience through just a pair of headphones.
But our test subjects don't know that. They think they're just coming in for a hearing test in a focus group.
When we bring them into our testing area, we have Bullet bark at them.
Then in the middle of our lame test, we introduce the surround sound of Bullet attacking them from behind.
But when they turn around, there's no dog.
It's just a grumpy-looking cat named Perfect. What's that? Oh, Edward. Yes. Congrats.
Okay, this is important. As they come
Audio
in,
test today.
this is what they see. The dog.
All right, just put those on.
Okay.
And just make that comfortable. Let's do it.
Hello. Thank you for participating in the DTS Audio Preliminary Sound Perception Test. We will begin by testing your hearing fidelity in each ear. If you hear a tone in your left ear, raise your left hand. If you hear it in your right ear, raise your right hand. Begin. For this next portion of the test, we will be testing your audio-visual location perception. You will hear a tone and its perceived location will move from side to side. Follow the perceived location of the tone with only your eyes. Begin. Thank you. For this next portion of the test, we will measure your frequency range perception. You will hear a series of tones varying in volume and pitch, and you will be asked to guess.
I'm sorry, that's
You want to take it?
For this next portion of the test, we will measure your frequency range perception. You will hear a series of tones varying in volume and pitch, and you will be asked to guess.
Okay, so what I wanted you to kind of notice is that those reactions were very, very real, but the sound was always being played over the headphones. But people really believed that there was a dog behind them that was going to attack them. Now, this example, I believe they have placed the cues, the normal HRTF cues, in the sound of the dog barking, so that it was very realistic. But the key thing is that as they move into the room, the first thing they see is the dog barking at them. And in psychology, that's called priming. that's planting an idea in your head that there's something there that might attack you, that dog. Now you kind of forget about that, but unconsciously you have it there, so that as soon as you hear the dog, you kind of go, oh, I know what's going to happen, I'm going to be attacked by the dog, and you jump up. So I wanted to look at that effect, and of course we couldn't do that at the university because there's ethical considerations to look into. But I wanted to look at that effect and try and measure it and try and prove that actually that exists. And that just by priming someone, that people will perceive sound being outside the head when indeed they haven't got any cues or any reason to believe that it is outside. So the research questions in this case are, can we associate externalization with plausibility, this effect? Can we associate externalization with oralization cues? Because I wanted to know what was the difference between having proper cues and having plausibility. And of course the full test, which is, can we associate externalization with the combined cues when we have plausibility and the oralizations being played through. So we need to present a number of scenarios to the subjects. We're studying the effects of headphones, so this is going to be on headphones. These are the independent variables, oralization, plausibility, and combined cues. And the dependent variable is basically seeing whether the subject reports hearing the sound outside the head or inside the head. We've asked it in a slightly different way, but that's the idea. In order to model the oralization cues, this is what we've used. Now we're short of time. This is research work that's well known. We can talk about it at the end if you want. But basically we've modeled it properly so that we had proper cues when we were using them. Now this is the actual test. We've asked subjects to come into a room and play this game, the snake game. I'm sure many of you will have played it. But it's basically something that keeps your focus. You need to keep looking at this computer screen and it kind of grabs your attention. You're playing the game. They were obviously wearing the headphones. And then in the room, what we've done is we have, beforehand, we've recorded some sounds that we were going to use for the test. Now, we recorded the sounds anechoically in our anechoic room, or we sourced them from libraries. And then, if we wanted to use cues, we convolved them with the room model, the HRTFs and the cues as needed. So it was a model of this room, so we get the right cues. But what we've done is, we sat the subject playing the test, but then we had a number of events which we call plausible events. And these are phone ringing, which would start ringing towards the back of the subject there. We had a mug which was placed on the table where they were doing the test. We had a ream of paper placed on another table back there. And we had the experimenter cracking their fingers in front of the subject as they were doing the test. Now, we also had what's called non-plausible sound events, which was basically a car horn, a door opening, a bike bell, and a mic stand falling over. And these were not in the room. Now, the key thing is all the sounds were being played over the headphones. All of these, the plausible sounds, were being acted. So when the actor would place the cup on the table, it would have a little rubber base that wouldn't make any noise, so they would just go like this, and the sound would play on the headphones. If they cracked their fingers, they wouldn't actually crack their fingers, it was just playing on the headphones. The same thing with the mobile phone. When the mobile phone rang, the experimenter would go to it and go, switch off, oh, I'm sorry about this, and put it back on the table. Now, in order to do that in sync with the sounds, we had a little screen behind the subject, where we had the waveform playing and we could see where the events were, so we could sync it up. So it was basically Foley type of work. Okay, so no sounds at all were in the room. Now we've divided this into two groups. Group number 1, 10 subjects, we played the plausible sounds with oralization cues and the non-plausible sounds without oralization cues. Now this is important because we don't want to play the same sounds to the same subject again because they've already got an expectation. So we needed to divide that in that way. So the other group, of course, had the other conditions. And at the end, we would ask the subjects to tell us, so we would have a list on the computer with each of the sounds, and the subjects would have to tell us whether they heard the sound in the headphones or in the room. And if they were in the room, then we'd still ask them whether they were perceived front rear, or right rear, or front left, or right left. We didn't use this data, by the way. We've just encoded whether the subject told us whether the sound was in the room. So if they said that that particular sound was in the room, we would count that as externalization. Now we've also filmed the subjects, and at the end of the experiment, we've asked them some questions. So when we looked at the film, we saw some interesting things. For instance, when subjects would hear the stimuli with no spatial cues, with no oralization cues, most of the subjects would look up from the computer and go, what's this sound I've just heard? Okay, with a kind of a puzzled face. We saw that quite a lot. But then as the experiment progressed, they stopped doing that. They found that something was going on and kind of left it. Now, if we had stimuli with spatial cues, subjects would look up and then they would look in the direction of where the stimuli was coming from. And that sometimes even included, you know, the car door and the horn and so on, which wasn't in the room. But the idea here is that they were actually starting to track the direction of the sound, even though the sound was being played over headphones. And some of the subjects actually stopped the experiment when they thought they heard the mobile phone ringing and they asked, should we continue? You know, are you going to take a call? So they really believed it was the mobile phone. It wasn't, you know, they didn't quite feel it was in the headphones. So these are the results, and that's the answer to the first research question. Is externalization associated with plausibility? Now here, we can't assure that we have normally distributed data. We have only a few subjects, only a few auditions. So we can't use parametric testing. In this case, what we do is we use a Pearson chi-square test of association. And it's basically, it looks at the counts, you know, the number of times that people said yes or no when it was with cues or without cues or plausible or not plausible. So it's still a statistical analysis, but it doesn't rely on normal distributions. And this is what we found. We found, okay, so the null hypothesis in this case is that no association exists between externalization and plausibility. And what we found when we looked at the data is that we can reject the null hypothesis. The association between externalization and plausibility is significant, and more than that, we've measured a medium effect size. So that's this number here, the Kramer's V, okay, of 0.29, which is considered a medium effect size. So fair enough, and we can see the data here. So here we've got not plausible without cues and plausible without cues, and we can see that when subjects report that there is externalization, of course we get a much higher count of sounds which are plausible, even though they have no cues. So this is really interesting. Subjects are telling us that they can hear the sounds outside of their head, even without any cues, just because we were placing the mug there and the mobile phone was ringing and so on. So they really believed that the sounds were in the room rather than on their headphones. Now, what about the association between externalization and oralization cues? Again, the same type of test. Association is significant, so we can reject the null hypothesis, and we still measure, again, an effect size, in this case, about 0.34. And when we look at the graph, it's the same kind of idea. So, when subjects reported externalization, we find that they reported it more often for the sounds which are not plausible with cues. Now, notice here, we're only including not plausible sounds, so sounds that weren't in the room. But because we were putting the cues there, they were being fooled into thinking the sounds were actually out there. Okay? So they were giving us positive answers. But perhaps what's more interesting is what happens when we combine the two effects, when we looked at the sounds which were plausible and had the cues on. Again, the association is significant, but now we've got a large effect size, so it's much stronger in terms of result. And it's basically telling us that if we put oralization cues and we plant the idea in people's minds that the sound is somewhere out there, that most of them will report the sound as external. So they get a really clear percept of sound outside their heads. I've done one next test which basically looked at each of these comparisons. So, not plausible without cues, and the number of people who said the sound was in the headphones or in the room. And then not plausible with cues, number of sounds in the headphones or in the room. Then plausible without cues, in the headphones or in the room. And then plausible with cues. And what we can see is a very clear effect, which is supported by statistical analysis, that if we don't have any plausibility or any cues, then most people will report the sound as coming from the headphones, okay? So not in the room. If we have plausible sounds and we put the cues, then most people will report the sound as being in the room, so a very clear effect. And if it's in between, then it's no different from just guess rate. So what we're seeing here is that the combined effect is the key thing to get the very, very clear percept of externalization. Which, you know, in terms of results, it's quite interesting because it tells us something else that we didn't know up to now about externalization over headphones. And that is that it's not only about the right cues, it's also about how much people expect things to be happening out there in the room. So this has got some really clear implications in terms of how you're going to use this for production, even for surround sound. You know, not only for oralization, but for surround sound, this is an important aspect. So we've seen that on their own, plausibility or oralization cues are only weak effects, but when we combine them, they are really strong, a much better perceptual effect. And, you know, producers, people doing, you know, sound art installation and work like this can start using this sort of idea to try and see how people respond to that. And, you know, I find it's interesting, but perhaps more... I find it intriguing. I find it that, you know, it's great to be able to play with people's expectations and go over even the kind of the accurate technological advancements and just, you know, play a bit with their, you know, expectations and perceptions. And that's the end, finally. Thank you very much. So I'm guessing some questions, if anyone has any questions.
En español o en inglés, la posibilidad de traducir. Si alguien quiere preguntar en español, se puede traducir. Como ustedes quieran.
Yes.
Very nice for your conference.
Thank you.
Very cool, very nice.
Thank you.
Why did you use bark? The last experiment.
Yes.
Why did you choose
Those sounds. Okay. I mean,
because I think for this experiment, for you, maybe it's more important the intensity. But from the point of view of the perception, maybe there are other kinds of stimulations, like emotions.
Yes.
For example.
Yes, 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 absolutely.
And they are different because emotion is very soft.
Exactly.
And
I agree, and I see your point. So the bark of the dog is very, very powerful because it incites that what's it called? Fight or flight reaction. That psychological. You know, I'm going to be attacked. What am I going to do? And that was very strong. The reason why we didn't use the bark was because ethically we couldn't. You know, we couldn't have a dog, and we couldn't. I couldn't get ethical approval for a test that would scare my subjects. You know, I might get a student dying of a heart attack in the lab, and then I'd be liable for that death because I didn't get ethical approval. Which makes the results all the more interesting because, as you said, the emotional impact of the sounds that we planted in the room are very low. You know, someone placing a mug, someone cracking their fingers, it doesn't incite any kind of, oh, you know, I'm going to be attacked. But we still measured an effect. So in hindsight, I think it was actually a good solution to choose much more watered down, non-emotional sounds. But of course, what I would like to do is a much more visceral kind of, you know, responsive. In fact, with one of the colleagues I presented this morning, we're doing some work on virtual reality with sound direction using wave field synthesis. And one of the ideas he's got is to have a little booth in a public space, say, you know, a supermarket or a shopping center or something like that, where people are invited to come and listen to our sound. And then what we do is we play a sound of a cat approaching really quickly, going like that. And because of the wave field synthesis, we can make a focused source appear like it's getting very close to you. And then the idea would be to film the reaction of the people and see how they react. But of course we can't do that because, you know, if someone goes in and gets really scared and topples over and hits their head on the floor, then, you know, we've got a big problem. But yeah, those kind of effects are even better. And of course we should explore them a lot more. Yeah, it's a good question. Any More questions? Yes.
I have a question. I don't know how exactly to formulate.
¿En español? Yes.
No sé.
Es lo mismo.
Dile en español, no hay problema.
Que lo como tiene que ver con which percent of the people in the experiment were actually affected and what percent were unaffected by the externalization on the headphones.
Okay. Well, those are here. So
I mean, in cases it was absolutely unaffected by externalization. I mean, people that didn't realize that it was something that had a telephone ringing
okay.
outside.
So, but you're saying in general, as a whole, a full count. Well, those would be here.
No, I think I mean.
Okay.
I mean,
Let me try.
there was people that didn't feel the telephone outside, for example.
Yeah, are you asking, were there any people that answered no? Even,
Absolutely.
yeah. I'm sure there were, yes, because the bars will tell us that. I don't know which individuals there are, but I could look back in their data and see whether, for instance, which is I think what you're trying to get to, whether one subject never really got any externalization. Yeah, that's what you're asking, isn't it?
Yeah.
So yeah, that's an interesting way of analyzing this data. I think I could plot for every subject the number of externalizations and see if there was anyone who never really externalized, so they weren't fooled at all. That's what you're basically saying? And in your view, why would you think that is important? What's the thinking behind what you're asking?
Because okay, I think really it's really interesting and amazing.
Yeah.
But when you study the person that is totally unaffected, we could try to analyze how to improve.
Yeah, okay, I see your point. That's a good point. I mean, yeah, I don't have a straight answer to that, but yeah, it's a good thing to think about. What happens to those subjects that they never get fooled? How different are they from
maybe
the others?
the perception of that person.
Yeah. It's a good point. Thanks.
I want to ask a more philosophical question.
Yes, I like that.
Because it's so hard that you get philosophy. Now you've shown us your research, which is very interesting, and you've talked a lot about applications.
Mm-hmm.
How do you conceive the connection between your work and the real world? Because you've talked about producers, you talked about, this is clearly, you've mentioned some applications.
Yeah.
How would you frame this work in connection with the real world, these two pieces of research you showed us?
Okay, what got me to do this test, and this is not the first test of its kind. I've been doing this kind of research for the last 2 or 3 years, but I've been trying to get to it from different perspectives and never really managed to put my finger on that result. Until the test just before this, when we were testing the same type of externalization but using a completely different methodology, which was basically speech streams, and we had them modeled and not modeled and distanced and not distanced. And then I realized that actually if we could somehow plant an idea in people's minds, we could measure externalization. We did it with an umbrella in the room where the umbrella would fall but only on the headphones, and we'd ask at the end, did you hear an umbrella fall? And where do you think the umbrella was? Was it in the room or the headphones? So, it was the kind of precursor to this experiment. But what got me to investigate this was, very often sitting, just listening to a film on a normal TV with no particular surround sound or pseudo surround sound, just stereo, and you're there, and then all of a sudden a mobile phone rings, a cellular phone rings. And your first reaction is, it's mine. Where is it? Where is it? Or some keys, or someone knocking on the door, right? And you kind of think, oh, is it on my door? No, it's actually in the film. So I felt there is a perceptual aspect, a cognitive aspect. Well, this is actually precognitive. There is a response aspect that will make us interpret a certain sound as being in a certain place, which is totally independent from the acoustic cues that are being placed to us. So I thought, how do I test that? Now, how is that then applied? Well, it goes back full circle. If a producer of a film wants you, and this is very basic, but I'm no producer. If a producer wants you to think that the surround sound or their surround mix is really good, then instead of trying to put, sounds which are not very easy to excite this response in their productions, they might just go knock knock just behind you, because that is an effect that it will startle you and it will make you think, oh, where is that coming from? So it's basically about knowing what types of sounds might be able to incite this kind of response. Now I'll just finish off that question with the next step for this is with Trevor Cox. We want to do this over the internet. So hopefully you guys can participate in this experiment. So what we're going to do is we're going to get this experiment on the internet, but instead of doing it like that, it's going to be disguised as a radio program. So we're going to have 2 or 3 different, very short radio interviews where one of my colleagues is going to, visit an expert and ask them, about mobile phone ringtones. So what do you think about mobile phone ringtones? Are they a menace or are they very good and so on? But before the experiment, we're going to ask the listeners to place their phone on silence and vibrate and on the desk in front of them, to the side, to the left. And then they can put their headphones and start doing the experiment. Then the experiment is going to run. They're going to be told that they just need to listen to some sounds and so on. We're not going to tell them what it is. And then just before the end, the mobile phone is going to go boom, boom, like that, sort of vibrating on the desk. And instantly we're going to ask the subjects, where do you think that sound was? Was it your mobile phone in the room or was it in the actual presentation? And we're hoping to see that when we prime the subjects into thinking that it is there, that they're going to say, I thought it was in the room, even though after thinking about it, it couldn't have been my phone because no one was ringing me. But it's that first reaction. And we're going to try to do that with mobile phones, a doorbell, and I think it's either a drill on the wall or some car door outside. And the idea is we're going to try and understand, whether we can reenact these responses often enough. And of course, this is not only for production and it's not only for surround sound, it's for the understanding of how we relate to sounds and how we know this from psychology studies. We fill in the gaps all the time. We think we hear everything very clearly, but we don't. We're filling in the gaps all the time. We're kind of putting things in our visual field that we think are there, but they're not. We all have blind spots and things like that, and we fill them up. I don't know, have you guys done the test with the blind spots? You've got, a piece of paper, you put a little dot on one side of the piece of paper, then you cover your eye, and you start pushing that piece of paper closer and closer to you. There's a point at which there's no point on the dot, the paper is all white. And that's because on our eye, we've got a place where the optic nerve connects to the visual cells. And in that place, there are no visual cells. So that's a blind spot. Now, what the brain does is, because it has 2 eyes, it kind of combines the images from the 2. But if you only have vision from one eye, the brain starts going, what's that? I don't have any information for that. Well, I'll just smear it with whatever is around. So you see a full white page. It's a really simple test. You could do it with a piece of paper now. And it's basically the brain filling in the gaps. And I think that's the same effect that's happening here. The brain is filling in the gaps. It's kind of saying, wow, where was that sound? This is a radio program. It can't be in the radio program, so it must be out there. So it fills in the gaps. It's quite interesting.
Thank you. I think we're running a bit out of time. Any other questions? Okay, so we'll just give
Thank you.